Hello everybody and welcome back to the second video on verifying trig identities. The reason that you see the same problem twice here is because I'd like to prove it two different ways for you. The first way, I want to start with the right side and then prove the left side. This one I'd like to start with the left side and then prove the right side. Remember from the last video that you never, ever work on both sides at the same time. Pick one and see if you can manipulate it to look like the other side. Okay? So if I looked at this first one and I want to start with the right side, I look first inside here and ask, can I combine these? Well, this is like saying x squared minus x to the fourth. I can't combine two things that don't look the same, so no, they're not like terms, so I can't do anything there. I do notice I have a squared term, which makes me think of Pythagorean identities, but I think that would just make it more complicated. So instead, I'm just going to distribute in the cosine of x. This is one way you can do it. So if I distributed that in, I would get sine squared x cosine of x minus sine to the fourth x cosine of x. And I want to see if that equals the untouched side of cosine to the third x sine to the sine squared x. Now, the idea of GCF is going to help us on this side. If I just took a cosine out of these two, it would end up looking just like the beginning step, which I don't want. But if I think about GCF in a larger sense, that I have two sines here and four here, I can take out sine squared, and I can take out the cosine x from both terms. So I ended up distributing it in just again to take it back out. Here's why it's useful though. If I take sine squared out of sine squared, that divides to be 1. Cosine out of cosine, that divides to be 1. So this just becomes 1 minus. If I take a sine squared out of sine to the fourth, I'm left with sine squared x. Cosine out of cosine is gone. So this side ends up, after you take out a GCF, giving me an identity here. But first, I'm going to leave this side alone. Okay. Now this side. I again know that sine squared x plus cosine squared x equals 1. So if I want to get 1 minus sine x, all I have to do is subtract the sine to the other side. So I know that cosine squared x equals 1 minus sine squared x. So I can replace this with just cosine squared x, and that is still multiplying sine squared x and cosine x. Here's some good news. One reason I thought about GCFs is a lot of the time when I use the greatest common factor, a good amount of time we end up getting a Pythagorean identity, which ends up helping me get rid of the subtraction sign, which you notice is not on this side at all. So let's take a look and finish this up. Sine squared is alone, but cosine to the first times cosine is 3 cosines, or cosine to the third. And so now I have that sine squared times cosine to the third is equal to sine squared times cosine to the third x. You can switch the order of these because you're multiplying. Verified. If I would like to do this problem a second way, what if I started with this side instead, and I would like to get to this side? Okay, let's see what we can do. The first thing I think about is I see a squared. So can I replace that with 1 minus cosine? Well, I could, but notice that this side has sines and cosines. So if I replace this with 1 minus cosine, this whole side would be in terms of cosine, which doesn't help me over here. So that's not my good first move. What I do notice again that comes with practice is that cosine cubed is really the same thing as cosine squared times another cosine, right? Because 3 of them is really 2 plus another 1. And then sine squared x is still there. Let me recopy this. So here, now that I've separated this into two types of cosine, I notice that I have another squared possibility. And notice I have multiple sines over here. So what if I replace this with 1 minus sine squared x from the Pythagorean identity, but kept everything else the same? Equals this. Okay, now I have a parenthesis if I replace that with cosine squared x, I'd be going right back up here, and that's not what I want. So what if I distributed this in? Because notice I have a subtraction sign over here, and maybe if I distribute that would help. 1 times this is just the same, cosine x sine squared x. This times this would be minus cosine of x sine to the 4th x. Does that equal this? I feel like we're close because we have the sine squared, we have the sine to the 4th, but the only thing how this side differs from this one is that this side has not yet taken out the GCF of cosine of x. So if I do that and I remove the cosine of x, I'm left with sine squared x minus sine to the 4th x. So now my two sides are equal. And if you wanted to even take it a step further, this original side had cosine in the back, and so you could rewrite this as sine squared x minus sine to the 4th x times cosine x equals the same side. So this would be verified as well. Again, this is a tough problem, but good the more times you practice it. And it's good to recognize that you could go either direction. My personal favorite between the two would be the first one. I feel like the idea of a greatest common factor at the beginning is a little bit more intuitive than knowing to split this into two and then use an identity, but I wanted to expose you to both. This last problem we will do together in class because I think it's a good problem, but if you'd like to try this before you walk in tomorrow, here's my suggestion. I would suggest starting with this side and using the idea of a conjugate, meaning a conjugate will remind you if you have 1 plus sine of x, the conjugate will be 1 minus sine of x. So consider multiplying top and bottom by a conjugate. Try it if you'd like and see if you can get secant of beta on your own. I will definitely take your ideas. Thanks, everyone.